Hi, today I'll be reviewing contrastive explanations for reinforcement learning in terms of expected consequences. This is by J. van der Waal, J. van der Gren, K. van den Bosch, and M. Nierensens. This paper is slightly older but attends to a crucial aspect of AI explanations, that is, the use of human understandable terminologies or concepts in the given explanations. Okay, before going into the details of the paper, I would like to give a short background on artificial intelligence explanations. So, you see, we need explanations for very critical tasks like high risk domain tasks in health and defense, or if you want to increase the model transparency, or if you want to increase the trust of humans on AI systems. The authors also take note of this very fact here, and they also mention that inappropriate trust in the output may cause substantial risks and problems. Now we can move back to our abstract. Here I've already highlighted the important parts of this paper that they're going to talk about. So basically this paper has three things to give. First is they explain agent behavior in terms of expected consequences. So expected consequences can be thought of as, well, I did this action because these are the consequences I was looking for, and therefore I had to take this action. Something like this is what their explanations would consist of. The second point is these explanations are in human understandable terminologies. Henceforth, we'll refer to this as concepts, that is, human understandable concepts. We'll delve further into what these concepts look like later on. Lastly, a very special note about this paper is that they can handle partial plans, like when the query is over a single action or multiple actions in a sequence. So humans are supposed to ask questions and they can query over, hey, why didn't you take left? Or they can query over a sequence of actions like, hey, why didn't you take left? And then why didn't you go right after that? Now for explanations with respect to this paper. This paper is dealing with artificial intelligence, that is the reinforcement learning agent, which is supposed to act in the world and somehow is able to, well, the aim of this agent is to gain maximum rewards. So you can think of it like as solving a game, and the agent needs to take whatever actions you can take in a game and finally win the game. Now, human can ask questions like why this action and why not this other action. These are two kinds of questions that they will be dealing with. First is something like why did you do the action move left? Okay, so if, let's suppose, although in this diagram the agent is marked to be here, let's suppose our agent was here. Okay, so the RL agent took the action left for some reason. We don't know why. Okay, and that is why we can ask questions like why did you move left? The second type of question can be, well, I as a human think that the agent should have moved right and maybe then right again. Okay, so I can ask, hey, why did you move left instead of taking right and then right? So this is the second kind of question, which involves a why not style of questioning. We'll look into the types of questions and how this paper deals with each of those types of questions. The first question, the why question, is fairly easy to answer in the way that this paper has described. However, getting to the second question, that is the why not question, is a bit trickier and requires a bit more framework. Before beginning with how we get to the answers of those questions, we can look at the parts required, the arsenal that we need to even begin. In this example here, you can see the human can ask question like why do you have to move up and then right instead of moving to the right until you hit a wall and then move up. You can see the sentence marked in blue is the fact, that is what the agent actually did, and the sentence marked in red is what the human expected the agent to have done. Now the blue sentence therefore will be called as the fact, that is what actually happened or the agent intends to do. The sentence in red would be called as a foil, that is an alternate plan or an alternate partial sequence of actions or the full plan or of action or maybe just one action such that the human thinks that this foil should have been done. So fact and foil are basically policies, but fact is a policy or a partial plan which actually happened and where my question lies as a human user, and the foil is the alternative that I think the agent should have done. Now, if you're familiar with reinforcement learning, then you know that the whole problem is that we formulate this problem as a Markov decision problem, which is defined by this tuple here. Now, the question is that we want this tuple to be interpretable. To highlight the issue, we know that this S, this R, these things are not understood by the humans. The state can be a sequence of raw pixels or anything, any internal variables of the system, or even the RAM configuration, which can be seen by a lot of Atari games that is given by OpenAI in its OpenAI gym. So those states are not interpretable by human. If I were to say that I'm in this state 0.2, 0.5, no one would understand what I'm talking about. Whereas if I say that I'm at index 1, 2, people would know that I may be talking about a Euclidean grid space and I'm at x coordinate 1 and y coordinate 2. So the goal is that we need to represent these states in terminologies which are understood by the users, henceforth concepts. Again, the second part is this reward function here. Now people may not understand what this reward is being given for. In reinforcement learning systems, rewards are given based on what the reward designer chose to solve the problem, whereas in real life, humans might not have the same model of the reward system as the reward designer had. So it is easier if we are able to explain that, hey, I did this because I'm going to get this type of reward in the future in terms that is understood by the human user. This paper does the first thing, that is to represent states in terms that the humans understand by the use of something known as concepts. The second thing, that is they sort of make this reward function understandable, is by achievement of some form of outcome. To give an example, let's suppose in my grid world here, my agent is at this location and I take the action right, and there is a monster beside me. Now the RL system might give a reward of say -100 if I take action right. Humans might not be able to understand, why this -100, why not -99 or something like that. So instead, what this paper suggests is we can talk in terms of concepts. That is, we can say, well, taking right will lead me to a state where monster present, this concept becomes true, and therefore I should avoid taking right. A thing to note here is that this paper requires that there must be a transition function available to us, which they state here. If it's not available, let's suppose my RL system that I had used is not model based, then this paper requires us to learn, that is to approximate a transition function. That's the first point. Now we'll look into what these concepts that we talked about are and what these outcomes are. As I said, the aim here is to get a user interpretable MDP, and once we have that, we can sort of use an NLP template and fill out that template using our user interpretable MDP to provide explanations. Now to get to that user interpretable MDP, what we need are two things. First is that we obtain a K, which is here. We obtain a K for K concepts binary classifiers, where each classifier says yes or no to each of the concepts. So let's suppose in my game here, I have concepts like I am near the wall, or I am near the monster, and so on and so forth. I can have a list of such concepts here, which can be either true or false, and therefore we can call these like propositions. Now what we want is to be able to predict that given a state, am I near the wall or am I near the monster? Now to get these concepts, what this paper does is, let's suppose, as I mentioned, there are k concepts, as in I1, I2, I3 and so on till ik. Now what we can do is, given a concept like near the monster, let's suppose this is some ij concept, what we can do is get examples from the environment where the agent is maybe here, or the agent can be here, or whatever qualifies as being true for this particular concept. And then we can train a binary classifier for each of these concepts, such that given a state, I will know exactly what concepts are true and what concepts are false. And in this way, we can sort of get a user interpretable state space where the state is represented by a list of concepts that are true in that state. The second thing that we require is a new transition function. So if you recall, the previous transition function, that is this capital T here, was based on this previous denotion of state action to state, right? But now what we have done in our user interpretable MDP is that we have replaced this S with a list of concepts that are true in that state. And therefore, we also need to change this transition function. Therefore, we get this new transition function, which is given by small t and is based on the concepts and give out the probability of some other concepts that is supposed to be true. Let's suppose if a concept left of monster is true and I take the action right, then the probability of dying is really high, because I'm at the left of the monster, and if I take the action right, there's a high probability that I will die. But note that all of these things that we talked about is not the actual state. Now given that we have these two things, that is k binary classifiers for each of our concepts and a new transition function like this, what we can do is extend our MDP formulation tuple like this. So previously it was SART lambda, and now we have added a list of concepts, list of outcomes that are possible, the transition function and k binary classifiers. So as we will note that these concepts or these outcomes are essentially the same thing. The authors also make note of this in one of their examples somewhere here, where they say that k can consist of a set of classifiers for predicates like next to a forest, wall, trap, or in the forest. We can apply these k binary classifiers to get whether these concepts are true or false in that state. Then we can define the word outcome in a similar fashion. That is, these outcomes can also be like, am I in a trap, or am I in the forest, or am I next to the forest? I think that there is only a logical difference between concepts and outcomes, in the sense that they're essentially the same thing, but outcomes are supposed to be concepts which become true when you take some action, whereas concepts are like property of the state itself. Now the authors here have differentiated between positive outcomes and negative outcomes here, purely for the purpose of filling out their NLP template that they define later on. Now given that we completely understand the notion of concepts and outcomes to make this user interpretable MDP, we are now equipped to answer the first type of query for explanations purposes, that is why action A, or why action A1, A2 and so on. So this type of question only deals with why did the agent did what it did, whereas the second type of question that we'll see later on also deals with why not this other partial plan or this other policy that the human thinks would have been better. This section here basically covers the why question. So we already have the agent policy pi, which is given by pi t. Now we use this pi t along with the transition function, that is the transition function based on the underlying states. This is the capital T and not the small t, to simulate this policy to obtain the effects or consequences. What this means is that I'll use this policy pi and the transition function and make many runs, make many simulations, and see which concepts become true eventually. We can get, in some sense, a Markov chain, or we can even get a single trajectory depending upon how we simulate. So if we take the best action always based on the policy, then we'll end up having a single trajectory. Otherwise, we can always get a Markov chain out of it. But finally, what matters is that we can convert all of this into a sequence of concept, outcome tuples, which look something like this here. They denoted by path. What this means is that in the presence of, concept CO, and when I take the action, so let's suppose this is my pi, which takes an action state S and gives out an action A. Now I've replaced this S with my concept list C0. So if I use my policy over this C0, I'll probably take action A, which will end up giving me, which will end up in a state where these O0 outcomes are true. You should note that this O0 is further defined as positive and negative outcomes which are possible. But again, to clarify, the positive and negative outcomes are only for the purpose of filling up their NLP template so that the human understands better for some reason. Otherwise, they can always use the outcomes and let the humans figure out for themselves whether the outcome is positive or not. So this is a kind of the NLP template that we have been talking about. So what these guys will explain to the human users is, for the next n actions, I will mostly perform this action A, and during these actions I will come across situations where these concepts will be true, and this will cause outcomes which are these positive outcomes and these negative outcomes. Or so this type of explanation is when you have the query based on only one single action, that is A. Otherwise, there is this second type, this second natural language template that they have for a partial plan. Something like, for the next n actions, I will perform A1 when this kind of situation is there where so and so concepts are true and so concepts, so and so outcomes are obtained. And I will take action A2 when I'm in this other situation where these other sets of concepts are true and these other sets of outcomes are expected. Finally, most of you might have figured out that these concepts come from the designer of the RL system, which makes it the bottleneck assumption for this work. Moreover, it also needs the designer to specify positive and negative examples, types of outcomes, like getting trapped is negative and achieving the goal is positive. However, this is purely for the purpose of filling up the NL template. Now this covered the first type of question, that is the why question. We will move on to the second type of question, that is why this instead of this other thing question. These questions are known as contrastive questions, where the human presents their own model of how they would have taken some sequence of actions versus what the agent did. So the idea here is that the agent should contrast the consequences. That is, let's suppose what the agent did is known as pi t, and what the human proposed is known as pi f, that is for foil, and I don't know what this t stands for, maybe the true thing that happened. Anyways, this is by agent and this is by the human. What we really need to do is contrast the expected consequences. So here in this why question, we saw that we can use a policy pi, simulate it, and get the expected consequence. That is, these sets of concepts are going to be true if I simulate pi t. that is if I follow pi t. This other set of concepts would be true, that is c0 dash, c1 dash, and so on, had I taken pi f. Now what we can do is contrast these two sets, that is, well, I did pi t, which is the agent policy, because these are the concepts that I wanted to be true, versus if I had done pi f, that is what the human suggested, then I would end up in a state where this other set of concepts is true, which I didn't really want. This is what they state here, where you can use a symmetric difference between the two things to explain the unique differences between both the policies. As you might have noticed, we already have pi t, so this part in this contrastive explanation is already solved from our previous discussion, but we do not have a pi f, that is, we only know a partial plan of what the human suggested. The human did not give me a function that can take any state and give out the actions. The human only gave me what to do in a partial sense, that is, in that situation what to do. I do not know what to do in rest of the situations. So a bit more work has to be done to contrast with what the user wants the agent to do instead. Now, since what we have been given is a partial plan or an action, this work tries to approximate a policy that closely matches with what the human wants. Hence, this policy, that we can call it as human policy or the foil policy, approximates human policy in some sense. Now, instead of learning the policy, what these people do is they learn a q value function and then they use that q values to get the policy. Now, as I said, the human, let's suppose in this example here, has only provided us with what to do in a partial sense. The human has not given us what to do in each and every possible state. So we cannot truly approximate what the human would have done in other states too. This gives these authors some motivation to use a mixture of the agent policy and the human provided partial plan. What this means is that, well, the idea is the new q function qf or q foil or whatever, this will adhere to what the human wanted wherever they have specified it, and wherever they have not specified it, this q function will try to follow what the agent did, so as to have a good contrast between the agent policy and the input policy. Probably this is what this I stands for here. Now, as we know, what we really need for us to completely understand this work is this pi f. For pi f, we know that what we need from this equation here is this qi. Again, qt is something that the agent had learned, so we already have this. qi is something that we need to figure out, and once we have this, we will have qf, and once we have qf, we can use this to get a pi f, and then we can contrast. So the problem now remains is to figure out what qi is. As I said, the idea behind qi is for this policy pi f or the q function qf to follow what the human said wherever the human said something. So what we would want to do is, let's suppose if the human said action af and action at was the action taken by the agent, we want to prefer this action af instead of action at. The way these guys do this is to give more reward when you take af instead of when you take at. An example here is, well, following their original example, that is, the agent did is move up and then right. What the human suggested is move right, and when you hit a wall, then you keep moving up. Now what we can do is, in this situation, what we can do is, when the agent takes this right action, we'll give more reward instead of when the agent takes up action. When the agent hits a wall, that is, this concept here is true, what we can do is give more reward when the agent takes up action instead of when the agent takes this right action. So the idea right now is, what we want to do we have two actions AF and AT. Whenever AF is present, that is, whenever the human has provided us with some knowledge, we want to give more reward to that knowledge instead of what the agent did. So in our equation, QF equals QT plus QI. This term is the term that contributes to providing more weightage towards the action AF. What this term does is provide more weightage to the action AT. This is because this QT terms follows the R when action AT is done. That is the reward. Well, it adds the reward when action AT is done. Now what we want this QI to do is weigh the action AF more. Therefore what we need to do is somehow add the reward for action AF and subtract the reward for action AT, and if we multiply it with some, say, epsilon or alpha or something, we can control how much we are weighing this AF over AT. This is the idea behind this equation. Well, an error I think in this paper is that this bracket should be an absolute value. That is, we are taking the absolute difference between what my current reward is, that is when I take AT, and what my reward would have been if I take AF. Now we can see how we can control this epsilon here or these other parameters or this weighted function or whatever to control how much we are weighing this AF action over AT action. Once we have this sort of reward function, we can use it to learn this QI, and then we can mix it up with this QT, which is from the agent, to finally obtain our QF. We can use whatever select action function that we are using over this QF. A usual way to do that is to pick the action which gives us the maximum Q value. We can do that, or whatever other method that people are using. We can do that to get our pi f, and then we have already seen how we can generate the contrastive explanations here. As I've already mentioned, that this paper can deal with queries that involve a single action or maybe a full-on policy. Now the results here in this user study, it clearly shows that people prefer this explanation which is based upon the policy. The user study also shows that people really love explanations which involve a lot of information. Well, my personal opinion is that when that information is structured, that is why people really preferred this kind of explanation strategy. In general terms, what I've seen is that people really like short explanations. They don't really need long lectures over their queries. However, their user studies show that this is the case here. This might be because of the domain they've chosen or some other reason, but I'm not sure why people would go with more information always, unless it is highly structured and the way human wants to see it. I guess that's about it for this paper. So in summary, the paper tries to explain agent behavior in terms of expected consequences. That is, if I take this action, these are the concepts or these are the human understandable terms that are going to become true, and that is the reason they say is why they took this action or why the agent took this action. Now, they not only explain the agent behavior, but they do so in terms of human understandable terminologies, which they follow from Hayes and Shah paper. Finally, a really good thing about this paper is that they can handle partial plans, and when the query is over a single action or multiple actions. Of course, something that is my concern and what they've noted out here as well is how much this approach can scale towards more complex and more sophisticated RL domains like Atari games. The second point is that even if it could scale, even then the RL designer is supposed to provide a lot of information like concepts and like outcomes, positive outcomes, negative outcomes, and things like that, which might not be feasible for all the domains. Nevertheless, this is, I think, a really good start in terms of explaining the way humans can truly understand